From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Last class I had 3 homework assignments left over, which wouldn't bother me, except one of these is still the one with no name, and so I'd like to have someone claim that today. It's 30 points out of 30 points, so it's worth claiming. So if that's yours, you can see me after class. Well, last class we were talking about coherence, and we will continue that today. And let's what it was we said last class, and for this, for the summary here, I've gone to the view graphs that I think most of you have copies of, although maybe you don't have copies with you, but in any case. We just said that the irradiance was the time average of E. We have 2 electric fields, E1 and E2, and then multiplying that by the complex conjugate. And working through here, we got that this was equal to I1 plus I2, 2 times the square root of I1, I2, times the real part of this thing we call gamma 1, 2 of tau, the normalized coherence function here. And we said that we could write this gamma 1, 2 of tau. I mean, it's a complex number, so we can write it as some magnitude. So the magnitude of gamma 1, 2 of tau, times e to the I, the phase, phi 1, 2 of tau. And then we said that, well, we could write that phase as a sum of 2 terms if we wanted to. We could write it as a sum of alpha 1, 2 of tau, whatever that is. We don't, right now we don't know what that is, minus some omega bar tau. And so this would be the average frequency times the transit time difference for the 2 arms of the interferometer. So this last term is just the phase that comes from the normal propagation. And this first term, alpha 1, 2 of tau, is something else. Don't know what it is, but maybe we'll learn something today about that. And then we come down here so we can rewrite this as irradiance is I1 plus I2 to square root of I1, I2. This is the equation that I hope you're dreaming about it. Again, last night, did anyone dream about this equation? No, I'm sure some of the people watching us on TV did. Anyway, so it's 2 square root of I1, I2, magnitude of gamma 1, 2 of tau, cosine of alpha 1, 2 of tau minus omega bar tau. And if we had the situation where I1 is equal to I2, then we could have factored that out, and we'd have 2, say 2I1 times 1 plus gamma 1, 2 of tau times the cosine. And so this gamma 1, 2 of tau, which we call the complex, well, called the complex degree of coherence, so the magnitude here is just called the degree of coherence. The effect of that is to reduce the contrast of the fringes. And I guess I lost a T here at the end. Actually, I lost a little bit here too on the printout or something. But anyway, that's the fringe contrast. It reduces the fringe contrast. And if the 2 beams have the same irradiance, the fringe contrast is equal to gamma 1, 2 of tau, or the magnitude of it. And so if this is equal to 1, we say we have complete coherence. If it's gamma is equal to 0, we have complete incoherence. And in between, we would have partial coherence. Now we had this phi 1, 2 of tau, which I don't know what happened to that view graph. It should be alpha 1, 2 of tau. We have this alpha 1, 2 of tau here. And the effect of that, let me change that. I don't know what happened here. The effect of that is to shift the fringes. Okay, we don't know what it is yet, but we see that the magnitude here will reduce the fringe contrast, and the alpha here will shift the location of the fringes. Okay. Well, we want to go on and look at this in more detail, and there are two separate situations that we want to look at here. We want to look at the case where we are going to have a point source, and so then we're going to be interested in temporal coherence, and we're going to look at the case where we have perfectly monochromatic, and then we'll look at spatial coherence. So we're going to go on and talk about temporal and spatial coherence. And for a point source, so with a point source, we're only going to be concerned with temporal coherence. We'll write that gamma 1, 2 of tau goes to, typically in the literature we just write that as gamma 1, 1 of tau. The 1, 2 will, the subscript here will apply to spatial coherence. The tau here will apply to the temporal coherence. And so for narrow bandwidth, extended source, and then often we'll just write gamma 1, 2 of tau as gamma 1, 2 of 0, because in this case where we have long temporal coherence, the time delay tau doesn't make any difference. Okay, let's now look at how the coherence function, what the coherence function looks like for a few examples here. And the first item we'll look at here is what I'll call this fringe visibility reduction. And break that into two portions here. 5.4.1 will be where we have a small source, broad spectrum, and so this will be when we're talking about temporal coherence. Okay, so we're going to do an experiment here. We're going to start off here with a point source, just say S, and I'm going to put it far away, and so the way I'll do that is I'll put in a lens here, and so the source is at the focal point of the lens, so I have a collimated beam coming out. Then I'm going to put in a beam splitter here, and I'll put a mirror over here, and some of the light's going to come up here, and let's say that this is where those two paths are equal, so I'll just draw a dashed line, and I'm actually going to put the mirror up here someplace. And so the paths are going to be mismatched by some distance x. Okay? Light comes down here, and I'm just going to focus the light on a detector. So this is the mirror's up here. This is, and the path difference is x here, or the round trip path difference will be 2x, because light will go up here and back. This is an interferometer. Later we'll call this a Michaelson, or probably we'll call it a Twyman green because it has a point source. But we'll worry about that in a later chapter, the name of it anyway, we'll worry about. I'm going to try to make it as simple as possible, so we're going to say we have equal intensities in the two beams. So I'll write that down. And if that's true, then we can write here that I is I naught, some number, don't care what, times 1 plus cosine of delta. And delta here is just going to be the phase difference between the two beams. And so we'll write that as 2 pi divided by the wavelength times, well, the path difference here, round trip path difference is x plus x, or 2x. So this is just the path difference. Okay. So we want to play with this a little bit, see what we get for a coherence function. Rewrite this just a little bit differently. We know that c is equal to lambda times the frequency, or 1 over lambda then is what? Nu, the frequency, over the speed of light, c. And so we can come up here and say, well, delta is 2 pi times nu over c times 2x. And so that's 2 pi times nu, but the distance it travels divided by the speed is going to be equal to the time. And this is the time difference that the light takes then in traveling the two different paths. And so that's, we're going to set that equal to tau. And I'll write that down again. So that's the transit time difference. And it's distance over speed. Okay. Well, okay. So now what we want to do is to, let's start off with a very simple, but maybe not too exciting, but we'll start off with it first anyway. And we'll start off with a simple case, unexciting case of a single frequency. And then we'll work our way up to an infinite number of frequencies in a while. But, so I is I naught, I'll just make it I naught of whatever the frequency is, times 1 plus cosine of delta. So it's cosine of 4 pi over c nu times x. What's that? What's
that word before time?
Tau here was the transit time difference. The difference in time it takes for the light to go the two different arms of the interferometer. And so that simply would be equal to the distance, the difference in distance for the two arms of the interferometer, so 2x divided by the speed, c. And so we will write this then in terms of tau. Oops, not an equal sign, but multiplied times here. 1 plus cosine 2 pi nu tau. Okay? And so we could rewrite this as I naught of nu times 1 plus, this is always true here, gamma 1, 2 of tau. And I shouldn't put 1, 2 because I'm interested only in temporal coherence, so we'll just make it 1, 1, or sometimes you'll just leave a subscript off. So magnitude gamma of tau, cosine of alpha 1, 1 of tau, minus 2 pi nu bar times tau. And I guess I need another bracket here too. Oops. So we just wrote that in terms of 1 plus the magnitude of the coherence function times the cosine of alpha minus 2 pi nu bar tau. And this here then is just the real part of gamma 1 of tau. Okay. So I warned you this was not a very exciting case where we had a single frequency. And so gamma 1 of tau equal, just write it gamma of tau, because we're not talking about spatial coherence, so I can leave the subscript off. And looking here, see gamma is equal to 1. Okay. And alpha 1 of tau is equal to 0. Well, I said it wasn't going to be real exciting. But this is what you would expect. We have a single frequency. The coherence function is 1. And the phase of the coherence function is 0. Okay? So any questions at this point?
What happened to C as you went from the first line to the second line?
What happened? I missed what you said.
What happened to the velocity of light as you went from the first line to the second line?
Here? Well, we had that tau here was equal to 2x over the velocity. So I just replaced 2x over the velocity with tau. So it's just the time difference it takes for the light to go the two paths of the interferometer. So single frequency, coherence function is 1, phase of the coherence function is 0, not so exciting. So let's go on and talk about adding together more than one frequency. And before I write down the equations for that, I need to digress for just a little bit here to kind of think about what we expect here. Now, when we interfere two beams, we always end up with a cosine of the phase difference between the two beams. Now, if the frequencies are not the same, part of this phase difference will be omega 1 minus omega 2 times time. Okay? So you have a delta omega times time. Now, if my integration time is long compared to the period of this beat frequency, then I'm going to average that out. Okay? So the average of the cosine of omega 1 minus omega 2 times time over sufficiently long integration time is going to become 0. And so the point I'm getting to here is that now when I'm talking about looking at more than one frequency in the interference pattern, all I need to do is to add up the intensities for each frequency. I don't need to worry about the interference of the different frequencies because that will average out. So, one approach is you can just add up all the electric fields and go through the process and then do the appropriate averages at the end. Or the approach that I want to take, because it's easier, is I'm just going to say right from the beginning that different frequencies, when they interfere, they're going to average out over my integration time. And so I only need to look at the intensities. I need to sum up the intensities for each of the frequencies. So in other words, what I can do here, if I want to go to the second example, which is going to be more exciting than the first example here, is that let's say I have two wavelengths, or two frequencies, maybe I should say. Nu1 and Nu2. I can write this as a sum, I write the intensity, or irradiance, as a sum of the irradiance for one frequency and the irradiance for the other frequency. And I won't have to worry about the interference between the two frequencies. So I can write that as some I naught of Nu1 plus I naught of Nu2 plus I naught Nu1 cosine 2 pi Nu1 times tau plus I naught Nu2 cosine 2 pi Nu2 times tau. So I'm adding up just the fringe patterns from the two frequencies, adding intensities. Okay? Everyone buy that? Then, to make everything as simple as possible, I'll say let I naught of nu 1 equal I naught of nu 2 equal I prime. And so the irradiance that I have here, I, then will be 2I prime times 1 plus 1/2 cosine 2 pi nu 1 tau plus 1/2 cosine 2 pi nu 2 tau. Okay. I'll give you a chance to get that written down. Okay, so everyone follows what we've done here. Now this is always equal to 1 plus the real part of gamma 1/2 of tau. And so for this example, this would be equal to the real part of gamma, only temporal coherence, so 1/1 of tau. So whatever this mess ends up being, that's equal to the real part of gamma. Okay. So now what we need to do is to play with this a little bit to determine the form of the real part of gamma. So first off, we know, maybe I'll bring this down, keep it in there for a little period. We know that the real part of gamma 1/1 of tau is equal to the magnitude of gamma 1/1 of tau times the cosine of alpha 1/1 of tau minus omega bar times tau. So I just have to play with this some way to determine what the magnitude is and what the phase is. So we'll take this and we'll use a trig identity that we used earlier in the class when we talked about superposition. And we'll rewrite that as I is what, 2I prime times 1 plus, remember when we added these, we ended up getting what, the product of the sum times product of the difference. And so that becomes cosine 2 pi tau nu 1 minus nu 2 over 2. Just what we did earlier in the semester. Cosine 2 pi tau nu 1 plus nu 2 over 2. So we have the difference here, and we have the sum there. So this guy right here is what? You know, it looks like this here. It's the average frequency times tau. And so, and this guy right here must be related to the gamma right here. And so we can say that the magnitude of gamma of tau is the magnitude of cosine 2 pi tau nu 1 minus nu 2 over 2. And it took the magnitude of that. So the coherence function here is going to go as the cosine of 2 pi tau times nu 1 minus nu 2 over 2. Now, the cosine itself, it sometimes would go negative. And when I took the magnitude here, I threw that negative away. But the negative really is related to the alpha here, because when this cosine goes negative, what do we know about the fringes? Cosine goes negative, the fringes are going to be shifted half a period. So in that case, alpha would be equal to 180 degrees. Okay. any questions on this? Coherence function goes as a cosine, 2 pi tau times the difference frequency divided by 2. And we take the magnitude of this, and when this, what's inside here becomes negative, it means the fringes are shifted half a period, and alpha then would correspond to 180 degrees. So it's kind of interesting that this coherence function here is periodic. Okay. It will go, depending upon tau, you know, it will vary in the cosine fashion, and it's going to be periodic. Now let me pick an example here. I'll show a couple pictures, and then I'll come back and we'll look at an example. And these pictures are things that you've seen before in the semester, because we used the same view graphs when we went when we looked at superposition. And so here we're adding the two sine waves with different frequency. And when we added them at some point, the visibility here would go to 0. So this would be as a function of tau here. So at some point it went to 0. And we saw that what we really had was something that was periodic, that at some points it would go to 0, and then some points it would be maxima, and then for other taus it would go to 0 again. Okay? So this is the same thing as what we talked about earlier in the semester in superposition when we talked about the beats. So let's go back here and look at this for a simple case. Let's say we have a laser as a light source, and we can get a small point source with that, so we don't have to worry about spatial coherence. And let's say the laser has 2 longitudinal modes. And I'll ask you, see if you, I don't know if you've had this in class or not, the frequency difference between longitudinal modes for a laser. Anyone know how that goes on? Maybe you haven't had it, but I'll tell you how it goes. It goes as c, the speed of light, divided by 2L, where L is the laser cavity length. So if we buy a cheap helium neon laser, one that has 2 longitudinal modes, we'll have 2 frequencies coming out, and we will pick a laser where they're polarized so the 2 frequencies have the same polarization, and the frequency difference would turn out to be c over 2L. So now I'm going to go back here and plug that in to my expression for the frequency difference and solve for where we get good contrast fringes. And so we would have here, whoops, better bring it down a little bit. We would have here 2 pi tau c over 2L divided by 2, so c over 4L. And this magnitude here will go through one cycle as this quantity here changes by m pi, 1 pi for one cycle. In general, this will be a maximum. The magnitude here would be a maximum when this quantity is equal to m times pi. And so then solving for tau, we have tau then is what? 2L m over c. And that's equal to 2x over c, the way we define tau. And so we're going to get a maximum in the fringe contrast whenever x is equal to an integer times the laser cavity length. Okay. So if I go back to my drawing here, we had this interferometer, and let's say we move this mirror back and forth, that whenever x, whenever x, the difference in the length of the two arms, whenever x is equal to an integer times the laser cavity length, we'll get best contrast fringes. Okay.
What over C?
2L was 2x over c. Remember that the round trip path difference is 2x, and so it's simply the distance divided by the speed. So that should be an x there, 2x over c. So whenever x here is equal to an integer number of laser cavity lengths, we're going to get a maximum in the fringe contrast. And it would turn out when x is equal to m plus 1/2 times L, the visibility will be a minimum. Okay.
Or do you have like a fundamental and little tiny?
Well, the question is that do these modes have the same intensity? And sometimes they have the same intensity. You'd have to make it, you have some gain curve for the laser, and you'd want to make the modes located under that gain curve symmetrically, then they'd have the same intensity. Whether they have the same intensity or not, you'll get the maxima and the minima of fringe contrast at the same location. It's just that the minima will no longer go to 0 if they don't have the same intensity. Okay. So you're an expert now on calculating coherence functions for two frequencies. We did it for one frequency, and then we did it for two frequencies. So I guess now we could go to 3 frequencies if we wanted to, and then 4. But let's take a giant step here right now, and let's go to an infinite number of frequencies. See what happens. And this becomes section 5.4.1.1. And we're going to call this Fourier transform spectroscopy. So we're going to do the same thing we did before. Just going to add up a whole bunch of frequencies here. So intensity is a function of tau. Well, we had one frequency, we'd say I of nu times 1 plus cosine 2 pi nu times tau. And now we're going to have a lot of these guys, so we put in an integral sign, 0 to infinity, and d nu. Okay? So adding up a whole bunch of frequencies here. And so we could rewrite this as integral from 0 to infinity, I of nu d nu. So I of nu is simply the distribution, the intensity distribution, and the intensity is a function of frequency here. So I of nu d nu plus integral from 1 to infinity of I of nu cosine 2 pi nu tau d nu. And then we could rewrite that as, well, let's just call this first integral here I naught. It's just the integral of all the frequencies, intensities, all frequencies over all frequency. So we'll just call that I nu. So then now this would be equal to, I naught. This would be equal to I naught times 1 plus integral 0 to infinity I of nu cosine 2 pi nu tau d nu divided by 0 to infinity I of nu d nu. So that's just some normalizing factor down here. And we know that this is always equal to 1 plus the real part of gamma of tau. And so this thing right here is equal to the real part of gamma of tau. Now this thing here, I mean, all this is a normalized cosine Fourier transform of the source distribution. So maybe all that Fourier transform stuff that Gaskell tried to teach you last semester, maybe it's useful for something. I don't know. Hope here. Okay. So did he tell you any jokes last semester? And then the next question, did he tell you any good jokes last semester? No. Okay. Well, I will just write down here, instead of saying the real part, I'll just say that gamma 1 of tau is equal to, well, we have this normalizing factor down here, I of nu d nu, and then upstairs here, 0 to infinity, I of nu e to the I 2 pi nu tau d nu. And so that's a normalized Fourier transform of I of nu. Okay. So what we can do here, I mean, this is actually pretty powerful. What we can do here, I'll give you a second to write it, and I'll sip some coffee while you finish writing it. So we could set up this interferometer that we had, and we could vary the path, so we're varying x, i.e. varying tau, and we would then will measure the fringe contrast, and we could keep track of the location of the fringes, so we know alpha as well as the magnitude of the coherence function. And then what we could do is we could take this gamma function, once we get gamma, is that we could take the inverse Fourier transform of gamma and get back to the source distribution. So we could say that I of nu is proportional to the Fourier transform, or inverse Fourier transform, if you like, of gamma 1 of tau. Okay? So we can measure what wavelengths we have present. And this is what's called Fourier transform spectroscopy. It works very well. Simply measure fringe contrast, Fourier transform that, and get back to the source distribution. Okay. Any questions on that? Okay, so that's something that works. Real life actually works very well. So we've looked at this thing called temporal coherence. I guess, there's one more thing I will show here. I sometimes give this as a homework problem, but I don't think I did this semester. But we said that for the case where we had a laser and we had two modes, that we got a maxima in the fringe contrast whenever the difference in the length of the arms was an integer number of laser cavity lengths, or I could say where the round trip path difference was an even integer number of laser cavity lengths. And we got a coherence function that really went as a cosine. Now it turns out, and this was a homework problem, maybe some of you want to work for the heck of it, is that if we have more than two modes, we say we have three modes, that we get the maxima in the fringe contrast in the same location. That's whether we had 2 or 3. Or if you have 5, you still get the maxima in the fringe contrast when the round trip path difference is an even number of laser cavity lengths. Or 7, same thing. And what happens as you bring in more modes, so you have more frequencies present, is that it becomes more critical to get good contrast fringes. It becomes more critical that you are close to this even integer number of laser cavity lengths, because the coherence function will drop off much faster as you get more modes. And if you kind of think to you had a homework problem this last week where you interfered 5 beams, And you're supposed to show that the radiance went something like, what, sine squared of 5 over 2 phi divided by sine of phi over 2. And as the number of beams increases, the fringes were getting sharper. So for 5 beams, you got much sharper fringes than you did for 1 beam, because you had the sine squared of n over 2 times phi. And it's the same equation, same results that you would get here for the coherence function. You would get the same thing of the n over 2 times phi type thing. And the fringes become much sharper, or in this case, the coherence function becomes much sharper as you add in more and more frequencies. And as it went to an infinite number of frequencies, of course, this would essentially become a delta function here. Okay? Well, you feel like you're an expert on temporal coherence now? You're ready to go on to spatial coherence? Okay. Well, let's go on and talk about spatial coherence. And for here, I handed out 3 handouts. I hope you picked them up when you came in. If not, you can get them when you leave. And those of you out in TV land, they're in the mail. How's that? And so we're going to talk about the case now where we have a broad source and a narrow spectrum. So this will be spatial coherence. And this is such a great theorem that we're going to come up with. We're actually going to give it a name, of the Vansittart-Zarnecki theorem. And I've heard that there's a rumor around campus, around optical sciences, that I really love this Vansittart-Zarnecki theorem. And if you ever have me on your prelims, you need to know it right and left. You need to know it very well. Because I do love this theorem. It's very powerful, very useful. So we're going to start out here. We're going to have some source back here in my squiggle eta space. And we're going to look at the coherence between 2 points here. One point having a coordinate x1, y1, and the other point having coordinate x2, y2. And this plane is a distance z0 away from the source. Now, some way we're going to combine these 2 beams and get interference fringes. And I show here maybe maybe this would just be 2 pinholes, and due to diffraction the beams will overlap and we get fringes over here. But this theorem is so flexible that it can be much broader than this. I don't care how you combine these 2 beams. You can have lenses, mirrors, prisms, all kinds of stuff over here. It doesn't matter how you combine the 2 beams. What we're simply doing is calculating the coherence between 2 points here, x1, y1, and x2, y2. Okay? And so I'll start off first. I have a single point source, and then we're going to extend that to a source of some size. But say that single point source, and so the irradiance at some point P here goes as I1 plus I2 plus 2 times square root of I1, I2 times the cosine of the phase difference between the 2 beams. And the phase difference between the 2 beams is simply K times R1 minus R2. So that's the path difference in getting to these 2 points. And then K times R3 minus R4. However we combine the beams here, is just K times the path difference. Okay? And we can write down here that R1 is Y1 minus eta 1 quantity squared plus X1 minus squiggle 1 squared plus Z0 squared. And we have a similar expression for R2. And I think maybe you're learning that I love the binomial expansion, so whenever I see something like this, first thing I have to do is expand it. Can't tolerate it until I expand it. And Z0 will be the large number here, so we factor Z0 out, and when we expand it, then R1 becomes Z1 plus y1 plus eta 1 squared over 2z naught, and x1 minus squiggle 1 squared over 2z naught. Similar expression for R2. And so again, what we're doing here is that we have a spherical wave leaving the source, and this expansion here is approximating that spherical wave as a parabolic wave. Okay? Any questions up to this point? Okay. Then what we're going to do is to make another approximation here. We're going to assume that eta 1 squared is much, much less than z naught lambda. In other words, we have, and squiggle 1 squared is much, much less than z naught times lambda. So we're saying that the region here is going to be a small region, because the source will be a reasonably small region, especially compared to distances and so on. And so we could go back and plug that into the R1 expression here, and simply we're throwing out the eta 1 squared term and the squiggle 1 squared term. And so we get this expression here for R1, and I probably should have written it down, but same expression for R2, except the y1s and x1s would be y2s and x2s. Okay? Then we take this and our expression for R2, and we're going to come back here and plug it into this expression right here. And we get a mess. I1 plus I2 plus 2 times square root of I2 times the cosine of this thing here. And so the R3 minus R4 we don't worry about. We don't care how we combine the beams. And the first term here, then we have an x1 squared minus an x2 squared over 2z naught, and minus x1 minus x2 squiggle over z naught. And what I've done here, we've taken this squiggle 1 and eta 1, and I've just put it for a general source point squiggle eta. So I got rid of the subscripts on that. And then we have a y1 squared minus y2 squared over 2z naught minus y1 minus y2 eta over z naught. And this is such a mess that I write it as A. Okay? Okay, so now this is the irradiance for a point source. Now I'm going to go to some extended source here and plug that back in to our expression here and integrate over the source. And so we end up then with a 2 times the integral over the source times a 1 plus integral of I squiggle eta cosine of Ka plus K R3 minus R4 integrated over the source divided by the integral over the source here. Integral of I integrated over the source. And we know that now we've put it in this form, we know that this is equal to something out in front here, some number, times 1 plus the real part of gamma. That's what we were trying to get. Okay? So we can say here that the real part of gamma, then, or we can say that gamma, not the real part, but say that gamma then is the integral. What's that? Oh, okay. So we can say that gamma here is the integral over the source of e to the I, Ka, and A was that mess we had before, plus K R3 minus R4 d squiggle d eta, and then normalized here. Now what we're going to do is we're going to rewrite this a little bit, and we're going to go back we want to play with A here. A was this mess we had right here. And one thing we're going to do is just say let x be equal to x2 minus x1. Let y be equal to y2 minus y1. So that's the difference between the x coordinates and the y coordinates of these 2 points. Okay? And let alpha sub x be equal to squiggle over z naught, alpha sub y be equal to eta over z naught. So that's saying that we're going to sit here, we're going to look back at the source and express coordinates in the source as angles. Okay? Angle alpha sub x, angles in squiggle direction, alpha sub y, and eta. Okay? So now we will plug this in to our expression for A here. And write down this equation down here. So gamma of 1, 2 of tau is, well, the R3 minus R4 terms do not depend upon the source coordinates. So this is independent of source coordinates. So that will factor out. So it's just e to the I k times whatever that, e to the I times whatever that phase is, the phase coming from however we combine these two beams, times e to the I. Well, there was a term here that went as x1 minus x2 squared and a y1 squared minus y2 squared. So they can be factored out. And so it's just some quadratic phase term here. And then we get to the interesting part of the integral here of I over I is a function of alpha sub x, alpha sub y. So function of the source coordinates in angular space. E to the I k, alpha sub x, x. This x right here was the difference in the x coordinates of these 2 points. And this y here is the difference in the y coordinates of these 2 points. And then d alpha sub x, d alpha sub y. So we're integrating over the source again. We have expressed the source in angular coordinates. We're integrating over the source. And then down here, we simply have the total integral over the source, and this is just a normalizing factor. Okay. Gamma 1, 2 goes as the magnitude here of gamma times e to the I phase. The phase is expressed in terms of an alpha 1, 2 of tau minus some omega bar times, I probably should have that tau instead of t here. And so the result here is that the coherence function, the spatial coherence function, goes as, well, we have this quadratic phase factor out in front, which often is not of much interest. And what is of interest is that we have this I, e to the I k, alpha sub x, x, alpha sub y, y, integrate over the source, and then normalized here. So the result is that the coherence function here, other than this quadratic phase factor out in front, goes as the normalized Fourier transform of a source distribution. So it's the same result that we got for temporal coherence, except here we're expressing the spatial distribution of the source and integrating, doing the Fourier transform over that, as opposed to before we were talking about the spectral distribution of the source and did the Fourier transform of that. So this is the so-called Vansittart Zarnecki theorem. It's simply says, I'll say it again, that the coherence function will go as the normalized Fourier transform of the source distribution. So do you feel like you're an expert on the Vansittart Zarnecki theorem? Well, maybe you have to think about it for a few more minutes before you become an expert. But I'm sure by next class you'll be experts. Well, this turns out to be a very, very powerful expression here. And I've had a lot of fun with it over the years, so that's why I love it so much. Okay. And I'm sure you're going to have a lot of fun with it, too. So I think, you go to Heck's book, you'll find a little bit on this, and you go back to Born and Wolf, and you'll find more on this than you ever wanted to know, probably. But it's a very good description of it. So this Fourier transform of the source distribution is a great thing. So I'm going to, if you're ready to go on, everyone ready to go on? Okay. Can't wait to go on, probably. Go on here. I'm going to repeat this equation, but I'm going to write it a little bit differently. And this comes from one of the view graphs. And so again, we have a source distribution I of squiggle and eta. And in this expression right here, remember that what we're doing is that we're sitting here where these 2 points are, and we're looking back here and expressing source coordinates as a function of angle. For this next view graph, we're going to write down the same equation, but we're going to be sitting back here expressing the distance between these 2 points in terms of angle. And what we had here was we have the distance between the 2 points being interfered times the source coordinate divided by z0. And we wrote that in terms of a distance between the 2 points, x, times the angle squiggle over z0. But now I want to write this as squiggle times the angle x over z0. Eta times the angle y over z0. And I'll call these angles here theta sub x and theta sub y. So they are the angular distance between points being interfered as measured from wherever the source is. And we just take our last equation and rewrite it, and we get, again, the Fourier transform of I of source coordinates, e to the I k, squiggle times theta sub x, eta theta sub y. And then integrating over the source and then normalized here. So it's the same result as we have here, except I'm expressing it in a different angle. One being an angle, here we have the angle, we're looking back at the source and expressing source coordinates in angle. Here I'm sitting where the source is, and I'm expressing the distance between the points being interfered in angle. Same thing. Okay. Sometimes one form is more convenient than the other. Okay. One other item here, picture. Again, this comes from the view graph. I think I stole this from Born and Wolf. Or maybe Heck, I'm not sure right now. But the interference fringe is obtained using partially coherent light. So here we're starting out, we have some source, And now what we're going to do is to vary. We have a fixed source here, and we're going to vary the distance between the points here. And look at how the fringe contrast changes. So for a given separation, we had a contrast of about 0.6. We increase the separation between the points. Contrast is going to drop. Increase it more, and the contrast will drop further. And again, if we measure the fringe contrast here, that's a measure of the Fourier transform of the source distribution. And so if I were to measure the fringe contrast as a function of a lot of different separations here, then I could take that fringe contrast and Fourier transform it backwards to calculate what the source distribution was. Okay. So do you feel puzzled? Yeah. Well, I think I expected you to feel a little puzzled. But I think you go back and you think about what we've covered here in class, and again go to Heck's book and go to Born and Wolf, and you will learn to love this equation. Okay. You will dream about this equation. You'll have nightmares. No, you won't have nightmares. You'll dream of. You'll love it. Okay. Well, that takes us on to kind of an application of this equation, and it was what we're going to call the Michaelson stellar interferometer. Michaelson was a very, very clever guy, and this would be 5.4.2.1. And he had a couple of interferometers named after him, and this is one that is pretty neat. So Michaelson stellar interferometer, and I didn't give you a handout of this drawing, but I'll let you draw it, and then we will describe it here. So what we're going to do, what Michelson's going to do, is he's going to put together this interferometer, and he's going to try to measure, say, the separation of binary stars. And we think of a binary star as kind of an interesting extended source in that it has 2-point sources, okay? And so maybe some way, if we could form interference fringes using this starlight, and we go back here and if we could look at this paper again. So what I'm going to have here, I'm going to have 2 stars here, 2-point sources. And I'm going to look at the fringe contrast here as I vary the separation between these 2 points. And let's see, the coherence function goes as a Fourier transform of the source distribution. And if a source were 2-point sources, Fourier transform of 2-point sources, I didn't take Gaskell's course, but can you help me? What's the Fourier transform of 2-point sources? Maybe you didn't take his course either, I don't know. What do you expect to get? Cosine, right. You're going to get a cosine. So the coherence function is going to be a cosine function. And so as we change the separation between these 2-point sources, the fringe contrast here is going to vary as a cosine function of this separation. And also will depend on this separation here. So what Michaelson is thinking, that maybe if I calculate or if I measure what the separation here has to be in order to get 0 fringe contrast here, I can probably calculate backwards as to what the distance is between the binary stars. Kind of follow that? So that's what Michaelson did. And his arrangement's like this. And as I said, I didn't give you a handout, so I'll make you sketch it. Here's his telescope. Okay? And Michaelson wanted to measure binary stars that were much closer together than what the telescope would resolve. And so he extended this. So he put, in front of the telescope, he put a couple of slits, and then he put a couple of mirrors here, and a couple of mirrors out here. And so now light could come in here and here. So it would come here, 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 and into the telescope. Here, 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 and into the telescope. And so he was able to get a much larger separation between these 2 points right here than what he could get if he just had a normal telescope. So we're saying here that in the telescope, the 2 slits in front of the telescope have a spacing of d, and these mirrors out here had a spacing of h. And what he's going to do is he's going to move these 2 mirrors back and forth, looking at the fringe contrast, and he's going to find what separation here gives 0, or at least a minimum, fringe contrast here. And he knows that the smallest value of h that first gives him 0 contrast here will correspond to the h that gives him the first 0 in this cosine coherence function. Okay. And if we think here for a second, you know, what does D have? What effect does D have on the fringes here? Well, D here determines the angle between the 2 interfering beams. And so D will determine the fringe spacing, because D determines the angle between the beams, so that's going to control the fringe spacing. H here will have no effect at all upon the fringe spacing, because the angle down here is independent of H. But H here is the distance between these 2 points here, and so H is going to, well, the fringe visibility here is going to depend upon H. So again, he simply will move these in and out, looking at the fringe contrast as a function of H, and determine where the minima is, and from that calculate backwards as to what the separation of the binary stars would be. And by being so tricky here, putting these 2 little mirrors out here, he could look at binary stars that was so finely spaced that they could not have been resolved with his telescope. So isn't that kind of neat? Michaelson was a very clever guy. So any questions on the Michaelson stellar interferometer?
Any of them work?
Yeah, they not only did they worked very well. And the amazing thing, not only could Michaelson make them work, but other people could make them work too. We don't have any astronomers in the class, do we? No? Okay. Well, we don't have too much time, but we'll start something else here. I'll go to a clean sheet of paper. Takes us to section 5.5, which is on fringe localization. Well, I did something tricky on your second homework assignment. Somehow I slipped in a question on fringe localization when we hadn't covered it yet in class. So that was good for you. It made you look at some books and stuff. And what we're going to do here is to go through and use this Vansittart-Zarnecki theorem to tell us where fringes are localized in space. And we're going to end up with a result that if we have a point source, fringes are localized every place the 2 beams overlap. And that was what you had to answer for your homework question. So you read that in Heck's book, or you read it in Born and Wolf or someplace else. It becomes trickier when you have an extended source, because now the fringes are localized, i.e. they exist only in certain locations in space. And finding out these locations is pretty tricky. And if you look in a lot of the textbooks, you'll find that there's all kinds of difficult geometrical proofs showing where the fringes are localized. But I love this Vansittart-Zarnecki theorem. And so back in, it's 20 years ago, it's hard to believe, 20 years ago I had this, if we could just show, this is the shortest paper I ever published here, half a page. But it shows that you can use the Vansittart-Zarnecki theorem to determine where the fringes are localized. And it drops out very easily, much easier than all the other complicated geometrical proofs that you might see out there. And so we have to start out here simply by writing down, again, the Vansittart-Zarnecki theorem, and then we'll see how it is we can use that to determine where the fringes are localized. And it will be so simple. We will unfortunately have to go back and use something we learned in Gaskell's course, but as long as we learn that, it's going to be very, very simple. So we'll just write this down again, the I, and I want to express it in alpha sub x and alpha sub y. So this is, remember, alpha sub x is the source coordinates divided by L here, L being the distance. I guess what did I use a minute ago? 0, z0, z0. And alpha sub y will be eta over z0. And so that's e to the I k alpha sub x, x plus alpha sub y, y. D alpha sub x, d alpha sub y. And then integrating down here, normalizing it, I of alpha sub x, alpha sub y, d alpha sub x, d alpha sub y. And we'll take the magnitude of this. And then what we're going to do is we're going to, I'm going to convert over from the alpha to the theta, like we had. And I think what I'll do, I'll put up a drawing here. Since I'm almost out of time, I can't go through this till next class. But we're going to set up our drawing here, where our source is here, we're over here, and we're going to express the coordinates over here in terms of these thetas that we already looked at. So the theta sub x would just be the difference in the x divided by this distance, and the theta sub y would be the difference in the y divided by this difference. And then we'll come back and look at the Vansittart-Zarnecki theorem in these coordinates, and bingo, just like that, we're going to know where the fringes are localized. But you're going to have to wait until next Tuesday to see that, I guess. So I'll see you on Tuesday. Who do we play tonight in basketball? Washington. Okay. So I'll see you Tuesday, and we'll see where the fringes are localized.